And Mike Whitehouse to come on. And Brian, please start by introducing yourself and who you are and how you've distinguished yourself in your career. I mean, you're one of the go-to guys. Tell us about Brian Dorwart. You're on mute.
It helps to get the mute off.
There we go.
It's a technical challenge. I'm Brian Dorwart with Brierley Associates. I've specialized in underground trenchless for quite a few years of different types of installations, specialized more in tunneling and in directional drilling. I've designed quite a few directionally drilled up to 54-inch, 4,500 foot long installations, down to I've done little 6-inch ones that might be 200-300 feet long crossing a road. They all have challenges, and that's the whole point of having team members. As I found as a designer, I need to consult a lot of times with the manufacturer, and in particular the fusion machine manufacturer, to make sure when I'm planning a project, you actually have room to build it. So that's always been the challenge. One of my favorite parts of being involved with HDPE installations.
Awesome. Well, welcome, Brian. We're glad you're here. Peter Nardini, welcome.
Hello, thanks for having me. So I'm Peter Nardini. I'm an associate principal with SGH and also the head of the Water and Industrial Infrastructure Division. So I've been working in all types of pipelines for about 20 years now, including HDPE. My work encompasses design, investigation, condition assessment, forensic investigations. So we've learned a lot from looking at projects, things that have gone well, things that haven't gone so well, and some things that tend to be tripping points in the designs. And we've seen some of the great advantages of HDPE, and I think we can talk about some of those today.
Yeah, look forward to it. Your color will be greatly appreciated today, Peter. Mike Whitehouse.
My name is Mike Whitehouse. I work for ISCO Industries. I would like to say thanks to ASCE, to the Alliance, and to my friends and cohorts over at Core and Maine for the opportunity and honor to be here and participate. I'm a geologist by training, and I found a happy home in plastics starting with ISCO in 1994. So like Rusty, I've been at it for about 30 years. I focus on burial and thrust restraint. I am a member with the ASCE Thrust Restraint Committee. Previously, before ISCO, I worked with AT&T and I did a lot of directional drilling. So I also focus on trenchless technologies and the environment, along with solutions to our global water crisis. Wow. And I'm happy to share what I feel I've learned and understand. I'm sorry, Peter?
Yeah, well, that's why you're here, Mike. And we're so excited that you're here with us today. And we kind of have a different thing, Mike, than what you're used to. We have more of a panel discussion that Alan Ambler's going to lead. But Alan, could you come on and tell us a little bit about how the bench works and what we look forward to on the bench?
So most definitely, if you've been with or through a Alliance for PE Pipe webinar before, we encourage everyone to ask any question that they have. Now, make sure you do so through the Q&A feature and not the chat feature. We do have a great bench here of support, aside from that silly guy with the hat on the right, that will answer your questions live as we go through. Now, if that topic and that conversation in question is really pertinent to what we're talking about, we may very well ask our experts to elaborate on that particular question itself. So once you do start rolling those questions in, we've seen as many as 80 to 100 questions come on as we go through, and we continue to answer those. So please don't hesitate to ask for that parallel channel of question and answer sessions, and these fellas in the background, and you, Peter, too, will be able to help answer some of those.
Well, thank you, Alan. About ready to turn it over to you for sure. And I want to thank our audience for staying with us here as we get through these opening slides. We've just found that these presentations go much better if we do take the 10 minutes at the opening to talk about how we construct these webinars. So take a shot of this page. This is everybody's email address. You can contact anybody in any order at any time. We are here to help. And with that, Alan Ambler, I'm going to turn it over to you, and have a great show, and I'll be leading the bench.
All right, Pete, thank you very much. And if you were chomping at the bit to come out and say anything, I'll certainly recognize you in that function. So it's not just our opinions as we present to you here. We've tried as hard as we can to make a industry-wide practice representation of underground installation of HDPE with thrust restraint. So the important part for that is the experts are here to really talk about that thrust restraint and anchor restraint and what's unique to HDPE. Here's some of the resources and sources we pulled information, technical information, and also photographs and videos to show you those things. It's one thing to talk about, it's another thing to be able to show you what happens in the real world, and the Alliance for PE Pipe certainly endeavors to try to do that to the best of our ability. So this is generally what we're going to talk about. Again, if you have a particular question that you want to ask us, this is one of those Ask Me Anything panel types. Definitely type it in. If you want to buy a cap like the one I'm wearing there, Thomas, you can certainly contact Richard Colassa. He loaned that to me, and he'd be able to help find exactly where that is for you in that manner. So even a question like that is definitely worth answering. Richard, why don't you come on? Because the next couple of slides are really for you. We're going to talk about properties unique to HDPE, that soil pipe interaction for traditional open cut construction. So this is open cut installation of HDPE pipe, which the Alliance finds is better than 2/3 of the actual installations within the United States, trenchless installations, and then thrust versus anchor restraint as we go through. So here, Richard, thermoplastic allows fusion. Go ahead and tell us what we're looking at here.
Yeah, thank you very much, Alan. It is important to understand these unique properties of polyethylene. This fusion process, of course, makes our connections, we'll say, not really joints because it's not really a joint. It makes it monolithic. As you saw in that previous slide, that's the fusion joint coming together in a molten state. So you get very good bonding between those two surfaces, not only mechanically, but physically and chemically. So it's kind of misunderstood. They said, well, that beautiful smooth surface is really nice to see. You don't want to see a concave surface in there when you're fusing, because that means you had pressure in that molten surface area and you've pushed that molten material away from the fusible area. So that's a really good example and picture of how that fusion takes place. So then we start, and this is pictorial way of looking at the fusion. You have two solid surfaces, you melt them, they become more amorphous and more relaxed, and then those crystals, they actually separate a little bit because they are frozen, so the density kind of reduces in that molten state. And then when you push those two surfaces together and they cool, they not only entangle, those molecules not only entangle, they also chemically bond within that, and then those structures go back to their normal state, which is crystalline and amorphous areas. And those little strands between those little round or circles are describing that area. And that these crystalline, are the straight line areas in this first area, and amorphous regions are the areas between those crystalline areas, which it's about 70 to 80% crystalline structure, will affect tensile strength, stiffness, chemical resistance, and permeability. And those are the key aspects of what your piping lines will actually, and how that piping line will perform.
So, Richard, this is a heavily engineered, from a chemical engineering standpoint, product. Is that correct?
Yeah, that's correct. I mean, you can think of plastics, anything from a low molecular weight in plastics such as candle wax, all the way up to our high density polyethylene pipe, which is very, very engineered. And it takes a lot of catalyst, a lot of reaction technology to put these polymers together to make sure that they are those crystalline areas are all uniform in size, so then you minimize the amorphous spaces between them. But then we also have technology to add comonomer into those amorphous areas to actually increase the amount of entanglement that we have between those molecules to give better strength, stiffness, and toughness.
So the Alliance does do a lot of education, and you can look at our YouTube channel. And Richard spends a whole lot of time telling us about the chemical engineering in that, but we're going to leave that right here on the table right now for what we've got. So, but you can certainly introduce this concept of viscoelastic behavior to us, Richard, and we're going to permeate the remainder of the presentation with this term in particular. So it can be somewhat difficult to grasp, but tell us about it, Rich.
Yeah, and you're not wrong about that. Viscoelastic behavior is behavior, especially on the yield point of the polymer. So before you have permanent deformation or breaking of those polymer chains, but you can have this creep or deformation effect underneath that yield point, where if load is applied or stress is applied, you can have strain deformation in this product that needs to be understood. And if you're underneath that yield point, then you need to really understand that you're rearranging the polymer a little bit, but when it's just like taking a spring and stretching it out. You kind of change the appearance of that spring because you're opening up that gap or that amorphous area. But then when you release that stress, then you'll have relaxation. So then you'll have a behavior that it will actually come back to its original state. Now, we've had lots of discussion about how much does it do it, how little does it do it. A lot of the testing that we've done with this unique property of high density with stress relaxation, if it is under very little stress, and let's say 10 to 30%, because you think about a horizontally a directional drilled pipe or a bursting pipe where you have tensile stress being applied to these pipes, then we want to make sure that that pipe relaxes and recovers to make sure it establishes its performance for pressure rating or even gravity fed situation where you don't want it to deform under soil loadings either.
Okay, we'll certainly talk about that more. Can you give us a little bit of information about Poisson's effect before we turn it over?
Yeah, absolutely. Poisson's effect is when we start up a polyethylene line, which we kind of learned a little bit the hard way. When we started connecting to more legacy products or Bell and Spigot products, let's say we drilled under a highway and then we connected to a legacy system, that we wanted to connect that pipe very, very quickly. And so we not only did we leave the pipe above ground where it expanded a little bit, but then we put it in the soil and it wants to contract. So we have an additional temperature stress that's added, but we also have, when we put it all together and we fire up the line and we pressurize it, we have a pressure vessel effect, which is Poisson's laws, where you'll have expansion of that pipe in all directions, which actually shortens that pipe. So this is a pictorial visual effect of that contraction. So we don't want to pull that Bell and Spigot that we're connected to, or the one or two sections that we're connected to in. So we probably have to restrain or put some kind of anchor system in there to stop that event from happening. So we can calculate those stresses and we can make sure that how far or how big those blocks have to be, which we'll get into detail later.
So, Peter, you brought this to our attention here. This is Performance Pipes 813TN, a technical note issues to try to calculate some of those pullout forces. Do you want to elaborate a little bit about this for us and how this might have helped you in looking at Poisson's effect and trying to calculate something in the field?
Yeah, sure. There are whenever we're looking at pipelines and longitudinal demands, we need to consider the effect of hydrostatic thrust forces, the Poisson's effect from internal pressure, thermal loads, any seismic demands. And specifically when it comes to HDPE, Poisson's effect is one of those items that's a little bit more significant to consider, because you have, as the pipe wants to expand, You develop a hoop stress in the circumferential direction due to internal pressure. And as a result of Poisson's effect, you develop a strain in the longitudinal direction of the pipe. And so if the pipe is not restrained at the end, it'll want to move. And so as Richard mentioned, if you're connecting to a legacy pipe or any kind of a structure that's sensitive to displacements, that movement may be problematic. And so in that case, you'd want to restrain the end of the pipe. And there are methods out here available for calculating the expected pullout force. And this is just based on your hoop stress from internal pressure, and then converting that to a longitudinal stress based on Poisson's effect. And there's some example of the magnitude of forces you may see here for different diameters of pipe.
So Richard, we commented yesterday when we were taking a look at this. This is a slightly older table, but still very much applicable. One of the reasons why it's slightly older is it shows a DR11's operating pressure at 160 psi when that's a 3408 or a 3608 material. Modern day materials are 4710. So over the years and the decades, Richard, that resin strength has continued to evolve and develop. Can you tell us what some of the differences might be in modern day resins versus this table that's slightly older?
Yeah, exactly. Well, one of the key differences of the two materials, 3408s versus 4710s, is one is a unimodal, which is your 3408, and one technology to produce the polymer. And the 4710s are a bimodal material. So we have two reactors in sequence to produce these materials. So what it really means is these tables are still applicable because of the density. The density is a function of hoop stress capability. So is molecular weight, but that's why you have a higher pressure in the 4710s than you do the 3408s. But that density value, you won't see a big difference in this. Do they need to be updated? Yes. But there won't be significant differences between them because of the functionality of density. So there's the aspect and the key difference between the two. But this is still a very, very good reference in terms of what those pressures and stresses will be on that pipe when you fire up that line.
So that difference is specific to this calculation as it's shown. There are many other developments within the resin progress from 3608 to 4710 that we certainly show much more recent material in using that as well. But again, there's tons and tons of material available for the Alliance for PE Pipe, and definitely take a look out there as well. So here we're attempting to quantify thermal effects for you. So these calculations came specifically from PPI's handbook on a polyethylene pipe for us. It gives us some great scientific foundation as to how to calculate what we'd see as a temperature change in the field. One of the things that the material of reference indicates to us is sometimes those field observations can be slightly different than what we see in the theoretical calcs. Sometimes the theoretical calcs assume instantaneous change. In other instances, if it's solar that's showing there, the bottom of the pipe resting on the ground may very well be different from the top of the pipe. And sometimes the fluid in between can actually change a bit too. So Brian, do you want to come on and talk us about this fourth bullet in particular, which happens to be the assigned number as theoretically proven? Can that be considered a working number, or how much more time should be spent in the field trying to see exactly and observe exactly what's happening with the HDPE? I believe you're still on mute, Brian.
Yes, sir, I am. Thank you. Yes, the thermal is very important for two reasons. In the trenchless, you can put a pipe in the ground and it's been sitting in the sun, and then you pull it through the ground, which is much colder, and you get to the end of your drill and you want to cut the pipe off and do something. Well, that pipe is still cooling off in the ground there. If you cut it off the rig too soon, your pipe's going to get sucked back down the hole because it's cooling off and shrinking. The other thing is if you have a are locked between two different manholes, you want to take into account what is your temperature when you put your pipe in. For instance, when we're doing pipe bursting with HDPE, we have a sun hit pipe on the ground surface. We pull it in and it comes out the other end of your burst. You want to be careful. It's going to shrink on you. It will shrink fairly quickly, but you want to be cautious that you take into account your thermal.
Yep, that's always good practice in pipe bursting, especially. We over pull. That way you're not ending up too short in what you have. Then once that pipe naturally relaxes, then you can come back and certainly make those final connections as we come through. Here's some of that theoretical as we follow through more with specific temperature change. So one thing that I've observed is a accurate estimation, well, accurate estimation, yes, of what could actually happen in the field as far as the temperature change that pipe might endure is pretty much important for what we're looking at. But one of the things that's unique about high density polyethylene is it does have a lower modulus of elasticity than other pipe material types, and that lower or a higher coefficient of thermal expansion, which will allow it to change more. So in this example, we simply did 2-inch DR11 HDPE and 2-inch scheduled 40 steel, 40-degree temperature change, 200 feet length. The HDPE would move 8 inches. However, it would take significantly less force in this 703 pounds to 8,400 pounds to restrain that pipe from moving. So this calculation is put through to get us a force over the actual wall thickness of that pipe as we look at it. And the expansion itself isn't a function of that wall thickness or even the diameter, as we'll see from the very next example, that the 10-inch DR11 at the same length will still expand the same amount, but generate significantly larger forces because we're transmitting that stress across the cross-sectional area of the pipe itself. So those are certainly unique properties to HDPE, and we'll talk a little bit more about some of this later, unless somebody wants to add something in particular. Nope. Okay, great. So here, Peter again brought us this slide as some things that are unique to high-density polyethylene versus other pipe material types. And Peter, please tell us why you thought that these were good bullet points for the audience to understand, and we're going to further elaborate on them throughout the rest of the presentation.
Yeah, absolutely. And I apologize, doesn't have the graphics on par with the rest of the slide deck. But there were a few points that I wanted to make sure to bring up today. As I said, when we think about longitudinal analysis of pipelines, we're looking at hydraulic thrust forces, thermal loads, Poisson's effect, seismic. We've already touched on a couple of the unique aspects for HDPE. And the first bullet here is the thermal load. It is significant and needs to be incorporated. And I think the major takeaway that we hope folks have is if you let the HDPE move, it wants to move quite a bit, but really it takes a pretty low force to restrain it. And so, from a design perspective, we should be thinking about, if we have a long run of HDPE pipe subjected to a thermal load, we should really think about restraining it. The force may not be that significant. If it's just a short run of pipe, maybe the displacement can be accommodated. The second thing I've kind of jumped toward the end a little bit, because the Poisson's effect we've talked about already. The Poisson's effect has a couple of impacts. One is it again, the pipe will want to move longitudinally if it's not restrained. So you need to be concerned about pullout, and then also if you're going to prevent that movement, it needs to be included in the forces for your anchor design. And then in the middle here, I think when we think about longitudinal restraint of pipelines in general, we need to really be careful with these hydraulic thrust forces and make sure that we have a good load path. So when we're looking at HDPE, it's a continuous pipe material. We looked at the fusion connections. So the pipe is continuous, and when you're looking at a below grade application, the the thrust forces in the pipeline are really transferred to the soil through bearing and through friction. If you're looking at above grade pipe, maybe you have to transfer those loads to some anchor supports. So we just need to be careful if there's any interruptions in that load path. If your load path is through the pipe to either an anchor support or to the soil through friction, we need to be careful to make sure we don't have any fittings or connections in there that can't take the demands. But as long as we maintain that continuous load path through the pipe, the HDPE can take the demands and transfer the load directly to the soil.
Okay, so that monolithic system is what the HDP industry likes to call it. All of those butt fusion joints are considered to be fully restrained joints. So when we put that HDPE in a line between two manholes or whatever linear installation we're seeing, any thermal or Poisson's effects occur across that line. One of the things you had indicated was sometimes when we have that soil embedment, that provides enough friction force to really restrain or stop sections of it from moving, which we'll elaborate on open cut. But is that do I have that summarized correctly?
Yeah, I think the for buried piping systems, and it can be done in other pipe materials as well. If you're using restrained joint systems, you're transferring the load from the pipe to the soil through friction. So if you've got a good installation with good compaction and a high coefficient of friction, yeah, that force is transferred directly to the soil.
So a big difference between that and a bell and spigot joint is because that joint is as strong, if not stronger, than the pipe itself, it still has all the tensile force allowable. But a tensile force that's in a bell and spigot system, you don't have that tensile yield there. So that's a prime way to think about the difference, maybe, correct?
Yep, absolutely. If you're trying to transfer any force through a bell and spigot joint, you're just going to end up with pulling the joint apart.
Okay, so we got a couple of great questions, and I'm going to get two of them live here real quick. We had one question about thermal effects for HDPE as installed through open cut construction. So the earth, once we've dug through and installed the pipe through the earth and we have a stable environment in the ground, there typically will not be any amount of substantial temperature change unless the fluid conveyed through that pipeline changes significantly. The two primary areas as to which we worry about thermal constraints is a temporary condition for moving the pipe above ground when it could be hot to below ground while it's being installed until that's stabilized. And the other is changes in the fluid as it's conveyed through there. So that's a great question. Thank you for giving that to us. And then we got another one. Is there a long-term elastic modulus and a short-term elastic modulus where we should consider for HDPE? And Mike Whitehouse, do you want to take that maybe with some color for Brian as to where we would try to estimate those and how they'd impact the industry?
Certainly. Appreciate that, Alan. Typically, you do have a long-term and a short-term modulus. And if you have a seasonal change where the environment is primarily responsible for your delta T or your change in temperature, you typically will use a much lower modulus than if you are in an Arctic condition in the polar region where you have a piping that connects to a tank, and that tank has a float in it that will send process fluid down your line, and that tank is holding at 120 degrees F, and your effluent is coming out very hot while you're in a cold environment. In those applications, it would be prudent to use a very high or an instantaneous modulus because the material is going to be changing temperature very quickly. If the change is occurring slowly through seasonal, it's much more gradual, and typically 50 to 55,000 psi is used for a seasonal change in the material, whereas more like 120 or 130 would be used for instantaneous. Another thing that I'll point out is since the polyethylene is self-restrained, it really doesn't hurt the piping material at all if it moves underground. In fact, it moves above grade all the time. It's only when it connects to end connections, fixtures, or dissimilar materials that might get pulled out that you need to start to become concerned with thrust restraint. And I have a lot of people that are asking me about, well, what's my force and thermal changes on this pipeline? I'm expecting an 80-degree F thermal change. And I look at it and the pipe's below the water table. And I'm like, your water table is a tremendous heat sink, and you're probably not going to realistically see an 80-degree F thermal change if you're indeed below the water table. Now, I'll be happy to give you a theoretical load based on that 80 F thermal change, if that's what makes the project successful, but it may not be a real design question when some of those come up.
Yeah, just to add to that a little bit, the thermal changes on short-term installations, like say a trenchless installation, those you would use a higher modulus on. Whereas if your installation, say some pullbacks for directional drilling might take 30 to 40 hours, you'd use a slightly lower modulus. And this information is heavily discussed in the PPI manual, and most manufacturers can tell you how much the modulus can change. So use the charts and figure out your time factor. Other things, if you have a non-pressure pipe as a gravity pipe and it's in the ground below the recommended depths for no concern, you start getting into a area where you start deeper and deeper installations, considering your soil loads on your pipe for long-term loads, because as that pipe creeps, if your soil is really soft, like just silts in a river, the pipe can start deforming over time. So you want to look at your modulus, which includes a creep factor. It's not really a true modulus. As far as design's concerned. So you want to look at all these things to see if your pipe is really going to be stable under the conditions, the low conditions you have in both short-term and long-term. Because a lot of times the engineers sort of forget about the long-term. So time factor is important on these as well.
So, Brian, we had a question specifically that says, how significant a concern is restraint if the pipe is buried underground and not pressurized in comparison to Poisson's effect? What advice do you have to avoid restraint issues for non-pressurized buried pipe? Does this change for very large diameters such as 63 OD? So if you would like to elaborate on the current, we'd love to be able to hear what you have to say for that question in particular.
Well, if this is installed in a open trench and then backfilled and compacted, there's really not a lot of change on the strength. It's going to pretty much stay fairly constant, and the soil is going to have enough resistance in it where even if you were to assume a fairly long frictional debonding, that strength is really not going to be exceeded. And you got to look at it in terms of stress and strain and strength. They're all interrelated. Well, if that pipe shrinks, it's going to create strain in the pipe, which is going to create a stress, which is your thrust restraint or your anchorage, restraint value. So does that really change? No, the strength pretty much stays the way it is, but the strength also has a time factor on it, being that the plastic is again a viscoelastic plastic. If you hold the pipe long enough, it's gonna start deforming even under that strength. Is that a problem? Not for a gravity system. You can get a lot of theoretical issues, but it's not something I really get too excited about. In a HDD trenchless installation, I would start getting excited. The strength doesn't really change. Say you have something in there for 20 years, you take the coupon out of that, and you'll probably, once you relax it, you're going to have the same strength of material. The material actual strength doesn't really degrade with time.
Okay, great. Just on your screen here, I did bring up some of the tables about the changes of the apparent modulus of elasticity over time. So as Brian mentioned, that is well documented, and they are available for you in PPI's handbook. We did have a fairly basic question, and sometimes we take some of those for granted. I knew nothing about running a utility before I started the city of Castleberry as a utility manager there, and I looked at everybody and said, "Hey, take me out in the field and treat me like I'm a kindergartner, so I don't, know anything." So we certainly learn more back from the basics. So Peter, if you can come on and talk to us now, there's a difference between thrust blocks and anchor blocks, and we'll get into that a lot later. But sometimes you would thrust block a PVC pipe for changes in direction, but you don't necessarily have to do that for HDPE. Do you want to elaborate a little bit for us on that?
Yeah, I mean, fundamentally, the way you can provide thrust restraint is either through providing restrained length on your pipe, or providing the force is transmitted from the pipe to the soil through bearing and friction, or through the use of a thrust block. And the thrust block is just cast at the elbow and transfers the thrust force directly from the elbow to the soil through bearing. And the purpose of that, providing that load path, is for pipes that have bell and spigot type joints. So you're not transferring the axial force through the pipe, because that axial force would disengage those bell and spigot joints. So for that type of pipe, the bell and spigot joints, the thrust restraint mechanism for pressurized pipe is going to be a thrust block cast at the elbow.
Okay, great. We're going to keep going here. Show you some things about open cut installation. Now, ductile iron, PVC, and high density polyethylene are all considered to be flexible pipes when we just look at the trench itself and how we're installing it. So any load that's put on the top of the pipe itself is transmitted equally to the soil surrounding it through this stabilized passive resistance. So it forms a pipe stiffness and a soil stiffness that really work together in order to be able to share the load through that. Those are different from rigid pipes, which are that hoop stresses or strength is considered to be significantly higher than the weaker soil, in which case that pipe is tasked to be able to direct all of the load that's on top of it to the soil underneath it in that manner. So it's interesting to note that even though that hoop strength or elastic modulus of HDPE is significantly less than ductile iron pipe, that interface as to which it makes with the stabilized soil surrounding it makes a big difference. Now, this is very different from a thick wall HDPE pipe, such as a DR7 or a DR11, all the way to a DR32.5, which is much thinner wall. And we've had some discussion about that thin wall non-pressurized pipe, and we'll do our best to try to continue with that still. So, Brian, I'm kind of go through and eke through this one while I want you to talk about it and elaborate it. Now, everybody on the call, we do have 30 minutes left. We do have some slides to get to, but this conversation warranted extra discussion, and that's kind of the reason why we're making our way through it in this manner. Brian, go ahead and tell us about what you see here.
Well, what we have is a viscoelastic performance of stress versus strain. Stress is force and strain is stretching one way or the other. You can see the elastic material. That's if you have a perfect elastic material, like steel is an elastic material. It'll increase very linearly in the strain, or it'll stretch very linearly as you apply more and more force until it gets to exceeding its strength. And when it does that, it starts curving over and eventually it pops. Viscoelastic plastic materials, and it's not just HDPE. You can look at rock salt. Rock salt's a viscoelastic as well. It means it's going to creep. And the creep will cause that elastic curve, instead of being straight, to start bending over with time. So you're stretching on it. The modulus, which we use for design, you want to take into account the creep, and the modulus in the charts does take into account creep. It's part modulus of the material and it's part creep. So if you have a constant load on it over time, it's going to continue to move until it can balance it. And that's what these different curves show, is as you increase the amount of time, those curves show that the creep has more and more effect. In other words, it strains, it stretches more. Doesn't necessarily mean the strength has changed, and it doesn't necessarily mean the modulus under the elastic portion has changed. However, the modulus for your design will be, you have to take into account the creep factor, and that's what the modulus and what this chart shows. You treat it differently than you would an elastic material. The whole idea is understand the material, design the material for the properties of the material, and you'll be fine.
So when we translate this concept to that open cut construction, and we have a balanced, supported, installed pipe with proper backfill, proper compaction, and safe loading conditions, then that creep is halted and stopped over time through its interaction with the soil itself. If we have a pressurized pipeline, in many instances, the loading that occurs on the top of the pressurized pipeline from external forces, it will be substantially less than what the internal pressure trying to get out of that pipe actually is. And I'll show you here in a minute as well for some calculations that we actually go through for the M55 manual to be able to show those actual calculations. So Pete, did you want to come on and say something?
Yeah, Alan, I would love for our panel to tackle this question from one of our guests. So it reads, are there any recommendations when considering Poisson's effect on a water main with hydrant tees? The hydrants need to be located in very specific locations. Do we consider the Poisson's effect when determining where to locate the hydrant tees? And my add on that question would be, does that creep, does that movement of the pipe affect that location, or does the soil load hold it in place? Peter, you want to take that?
Sure. I mean, I think when we have to acknowledge the Poisson's effect is there, right? If we have internal pressure in the pipeline and we have hoop stress, we have Poisson's effect. We can't get away with it, and it needs to be accounted for in the design. In terms of its impact on locating, hydrant branch lines, I think that it probably doesn't have too much of an impact on their location, but it may have an impact on whether or not you need restraint at those locations, if you need any kind of anchors. And you'd have to look at it on a project specific basis, look at your restraint you're getting from your frictional resistance, look at the bearing you're getting from the pipes, and see if you have any significant motion. And the answer may be that you don't, especially because if you have T's, you're going to have Poisson's effect acting in opposing directions on each side of that T, right? So it may be that you have opposing forces that balance one another. So I think you'd have to look at it on a project specific basis, but certainly it's something that can't be ignored.
So as long as those connections to hydrants are fully restrained, such as using an MJ adapter or other mechanisms, that hydrant's simply not going to pull off or blow off. One of the things that I've experienced running utility was the location and spacing of hydrants for fire protection far outweighs any type of restraint that we'd look at. So that's probably going to drive it a bit more. Pete, if you want to work on pronouncing Johnny Condori's question in Spanish and bring that to us. We'd love to be able to hear that in just a moment. But I'm going to keep going here as we keep looking through. So I'll breeze through these ones fairly quickly. The terminology of pipe embedment materials has come straight from, of course, Amster Howard, one of our godfathers of trench design and understanding, with lots of good field work. What we're trying to do is prevent flotation, doing all these things, and we're looking at a solid foundation, bedding, embedment, and then backfill, and it supports all of these parts and pieces of the trench for us. So I'll play this video that shows kind of some people think it might be a generally archaic way of being able to install pipe, but I'll tell you right now, it's got a solid foundation. That's just undisturbed soil at the bottom. That's free and clear of rocks. There's a bedding, which is a soft portion there at the bottom of the pipe to make sure that that pipe, as it's put in the trench, it has something to be able to protect it from other things. And then we'll have a video later potentially to show the embedment process and backfill as we go through. And here we show this video to show some of the benefits of having long longitudinal areas, and the fact that we can put all this pipe in with just 2 people as it's working through there. This spot is in between a house and a hedge, so there won't be an H20 loading condition as we go through, and then we continue to look through in that manner. It is perfectly safe and perfectly acceptable way to be more productive in the installation of the pipe itself. I will point everybody on the call's attention to an M55 design window, and that's what we're looking at here. This was in the first edition of the M55 manual itself, and it shows 95% of the installations in between DR7 and DR21. If you have 3 feet of cover with an H20 loading, or 2 feet of cover without that H20 loading, and a max depth of cover at 25 feet, you're safe to be able to install this without any additional calculations. So that's typically what 95% of the installs are about, and what we really look through from there. Now we have progressed to the second edition of M55 with slightly more complexities in understanding of the soil conditions as they go through. And here's a basic versus an engineered installation. So this is a different format of that table, but some of the characteristics are all similar in that manner as well. Now, when we start to get into that engineered installation, we won't be looking at quite as well compacted backfill and other things like that. It is important for trench width requirements. For 3 to 24-inch pipe here in the middle, we want that OD plus 12 inches. And a lot of times just simply the backhoe bucket will be able to make sure that it goes through and opens us up the trench that we really want to look at to be able to successfully put in the pipe as to we're working with it. Now, an embedment requirement happens to be based on the size of the particles that we're surrounding that pipe with. And I'd be happy to note here the 6 to 8 inch pipe for high density polyethylene is looking for a 3/4 inch particle size. And what that translates to in the field is they often put a 57 stone or gravel in the bottom of the trench in order to be able to stabilize the bottom of the trench to provide safe working conditions for the employees in the trench. That 57 stone is, of course, is what's sieved out to be able to provide that 3/4 inch particle size, and those are the same. So if you have a bunch of that on the site, it's perfectly safe to be able to put it through a 6 to 8 inch pipe surrounding that embedment all the way up if that's what you prefer and desire. So when we get up into a larger pipe, then we're looking at that slightly larger max particle size, and where the industry itself is trying to limit rock impingement on the exterior of the pipe itself. So that will be free and clear of other defects as we're looking for a better backfill embedment type condition to be able to come through. The 2 things that we're looking at for open cut installation happens to be a pipe stiffness factor factor, and then that soil reaction as we go through there. So as design engineers, we can make some estimations for what that soil reaction might be. And that soil is not only the embedment, but also how that embedment reacts with the trench wall. Now, it can be calibrated through field work, and we're going to get to a spot where Brian will elaborate on that a fair amount for us. These are some of the things that we actively try to calculate if we're outside of that design window, or if we have fairly challenging installations. They're all from some of that Iowa formulas, this deflection that we're looking at. One very interesting thing to note, and I won't go through wall buckling or some of the other ones, we'll go through some of the deflection, is that pressurized HDPE can withstand that deflection of 25 to 30%. When Brian and I were talking about this late last week, he's like, oh, oftentimes in the gas industry, you'll fully occlude that pipe to squeeze it off, and then you'll let it go to when you're ready to let the gas flow back into it, and it doesn't damage the HDPE pipe. We've had some questions about non-pressure applications, and some of that limiting factor won't necessarily be the deflection to yield to the pipe, but the operation of the system. So gravity sewer systems in particular, we want to make sure there's no sumps, there's no slumps or other things that would accumulate particulate material or something that would block up your ability to convey or require lots of cleaning to get through. The operation of the system for non-pressurized system controls much more than gravity sewer or the deflection of the HDPE in that scenario. Brian, was there something that you wanted to elaborate potentially on in some of this?
Yes, the whole advance from in M55 that Amster's developed is that there is a soil to structure, being the pipe, interaction. They do count. The other thing he found in his recent research is you can have a perfectly backfilled trench, everything in there just right, but if you have your native soil outside your trench that's really soft, that's going to impact your trench fill. The thing that the trench fill brings to the table, though, is it's usually a granular material, which means that the deflection of your pipe, the ovalization, is going to occur usually just during construction. And once the soil is settled on the pipe, is ovalized a slight amount, the sidewalls of the pipe are now being supported by the soil. That action is not going to continue to progress. You have a single short term, the pipe may be slightly ovalized, and you can pretty much calculate that if you want based on the Iowa formula and what you have for compaction in the trench, and looking at the surrounding soil to see whether that trench fill is going to remain stable. The important part of this is if you have bad backfill, you forget to compact it, which sometimes happens, that material is going to start over time loading up on your pipe, and your ovalization will start occurring more in the long term. Is that a big deal or not? No, because eventually it's going to stabilize because it's, again, a granular material. But soil is very important, and that's where those the modulus E prime comes in. Amster has spent quite a bit of time determining with studies, with several hundred projects he's studied, what is E prime? E prime is a magic number to make the field and the calculations work together so that you can predict, which is the object of engineering. But you got to understand what E prime is. It's a correction factor. Amster has come up with a way based on field testing of here's different types of materials with different types of E primes given the density of the material and the grain type of material. So there's some good information in M55 on both compaction as well as native soils around pipe for trench filling. Recognize, however, also in the long term, this same equation gets used for pipeline rehabilitation quite a few times. It's one of the main formulas or base formulas for 1216 for rehabilitation or putting in CIPP liners. The issue there being you have now a trench that is stabilized. You're trying to put in a CIPP liner. If the pipe is in the trench and it's happy, in other words, it hasn't failed or anything like that, you really don't have any load. All the load on your CIPP is going to be carried by the host pipe. So the E prime is dependent on what the host pipe is seeing, so not necessarily on your rehab pipe. So just a caution I've seen over the years, but soil structure interaction, very important. And then you can assess whether you have a rigid inclusion, being a rigid pipe. If your soil is much softer than the pipe's going to behave rigid. If your soil is much softer than the pipe, like pond muck, you have a rigid inclusion pipe and it's going to behave that way. So use the appropriate equations for how you think the soil and the pipe are going to interact.
Okay.
So
one of the slides I kind of glossed over here shows us that pipe stiffness factor. So this does work with the exact soil stiffness that Brian was just discussing, and we'll see a fairly dramatic difference between a DR 7.3 and that DR 32.5. So when we start to look at that thinner wall pipe that's outside of that design window we were in reference to earlier, then yes, that engineered backfill gets significantly more important to us as we continue through it. So one of the things I'd like to note to back up what I mentioned previously is a live load on a pipe from an H20 box truck loading. If we are at 8 feet depth, the external load on top of that pipe is going to be less than 1 PSI. So all of the pressurized pipelines, when we're operating at 55, 70, or a design life for a DR11 pipe of 200 PSI, are now exponentially larger than that H20 box truck loading at that 8 feet depth. So there's quite a bit of difference between the two. Now, if you have specialized loading conditions for earth load, surcharge, or other, then we want to make sure we go through that. I'm not going to get through these calculations. We'll talk a little bit about HTD, Mike and Brian, if you want to tag team, but we've got about 3 minutes before we really should launch a little bit more into thrust restraint and anchor restraint and what the difference is there.
Well, the issue on this one, I'll just take the lead on the Miami Beach because it was my project. Very interesting project, 54-inch. We had to use DR11 and DR17. We mixed it up. We put because it was very limited availability of pipe, we put the higher DR at the bottom, lowest part of the bore, and then we use the DR17 on the ends of the bore, just sort of as a way to use what you got. The important part of this, we're putting in 3,000-foot sections here. We got to put valves in there. So we had to install the pipe, and then we had to have valves that had the strength to be able to take the Poisson, this being a force main, Poisson and thermal effects. And you have to look at the time that the Poisson is going to happen, which is the pump system. So that's your sequence of one Poisson is going to occur. And then you look at your temperature difference over a much longer wavelength. You'll have a temperature difference maybe over weeks or months. You take these into account when you design your restrictions for that valve to keep it in place. So that was the interesting thing is trying to couple these things together. The little mud puppy on the left there is just a typical telecom. It's 2-person operation, HDPE pipe pulled in. We did 1,000 feet of that and in about 2 days, and pulled in number of telecom ducts all in one shot. It cost more to get the permits on that than it did to pull it in. The nice thing about the HDPE, we're going through granular material, really nasty, cobbly boulder. The only material that we really determined that was going to be tough enough was HDPE. That kind of material can break PVC, and it'll gouge any surface and corrosion protection you have on steel. HDPE is the ideal component. We fused it all together, pulled it back in one shot in about 3 hours. It shows that bad conditions, toughness really does make a difference. I don't have a choice in directional drilling of what the backfill is going to be. It's going to be whatever's in the ground. So you got to take into account your toughness. This is just a sequence of directional drilling. It's it's a totally blind. You don't know what's in the ground till you drill through it. You drill through it, you make the hole the best you can. When you pull your pipe through it, you're going to have to consider what that material is there, because it's going to impact the pipe, and you can have, say, a large rock on it. Maybe it'll dent the side of the HDPE a little bit, but you'll still be able to pull through it. It'll still be functional. Here's the restraints, some of the restrained joints we had. I'm not sure if that's on, no, that is Miami Beach. That's where we're getting ready to cut in a T-section to cross over to a parallel pipe there. You can see we have quite a bit of restraint on that one section there. So anyhow, I didn't know if Peter's got a lot of experience in the construction end as well. These are just a couple of examples of trenchless installations. The only other one would be more of a slip lining or a bursting with HDPE. Again, you got your material around you when you're bursting. It's going to be left in the ground. We found that you can use PVC, but with HDPE, it takes a tremendous amount of abuse if you have a problem product, that hose pipe that you're trying to burst. The HDPE comes through, even if it gets some scratches on it, it's just not a big deal, mainly because it's a gravity pipe, so scratches you don't really worry about, only in pressure pipes. Then there's certain rules for depth. So with that, some of the surface problems and shallow insulations, I'll let Peter discuss that a little bit.
So we about 3:10 here. We've got till 3:15. We have done quite a bit of discussion on thrust restraint previously, and had well over 30 questions, which is fantastic for the audience as we keep going. Pete, do you want to lead us through this discussion? And Brian and Mike, definitely let's get that hand up and try to be as succinct as we can from leading the discussion and then commenting in our last 5 minutes, because we do have some cool stuff to go through. That's the difference between thrust restraint and anchor restraints. And I've given you this picture here to kind of lead the narrative for us, Pete.
Okay. Yeah, and as you said, Alan, we've talked a little bit about thrust restraint as we've gone through here. And one thing that I want to highlight, similar to how Brian mentioned for ring deflection, you're really looking at a soil structure interaction problem. It's similar for the longitudinal demands as well for the thrust restraint. The stiffness that you're going to get from your soil, the resistance you're going to get to lateral movement into the soil is dependent on both your embedment materials and your native soils. And so you've got to be especially careful when you're designing thrust restraint for pipelines in very soft native soils. And we've certainly seen that. And so, look, I like this image. This configuration is interesting. It shows both buried HDPE pipe with elbows as well as above grade. And I think as we've discussed a little bit, for the buried HDPE, it's continuously welded joints, continuously fused joints. And so we have a continuous pipe to transfer the forces to the soil. Now on the above grade pipe, is where I think as designers, we need to be a little bit careful. This is an interface, right? So we're interfacing between the HDPE pipe and maybe some other material that's above grade, maybe that other material is designed by others, but we still have forces here that need to be considered for this connection. And so you've got the hydraulic thrust forces, you've got some thermal loads. And so we need to make sure we have good communication with the designers of whatever it is that we're connecting to here, to make sure that we have a good load path. It could still be through continuous pipe above grade. You know, if you're connecting to some kind of a steel pipe system, most likely that can take these longitudinal forces, but it's just a conversation that needs to be had, how you're dealing with these forces and how you're eventually transferring them back to some kind of a support.
Mike?
Yeah, I'll add a couple of things. First, it all comes down to the pipe soil reaction. So it really becomes more of a geotechnical challenge than a pipe challenge. It's easy to determine the stress in the pipe wall. And if you're in low strength materials, such as class 3, class 4, or 5, you have less support for your pipe. Your pipe stiffness plus your embedment stiffness has to prevent deflection beyond allowable limits. So when you go to the granular materials such as compact or crushed stone or sands, you're not only raising your modulus of the surrounding materials, you're also providing higher confining strength or stress to the pipe, and you're also creating greater friction. So if movement of the pipe is of concern to you, using a design fill is really important during construction. If movement isn't as big of a concern, perhaps you can save money on the design fill and use the existing soils. But if the existing soils have lower E prime values, they're going to provide less support to your system. And the things that make polyethylene so advantageous to the trenchless technologies are the same things that make us so successful in the seismic applications. And that's that we have a very high allowable bending strain. We have incredibly high toughness, or the ability to absorb impact and energy. And we have more than sufficient tensile strength to allow us to keep the piping system together. And the fused joint, once it's executed it correctly, is the same hoop stress and the same tensile strength as the parent pipe itself. And that's something that's very unique to polyethylene.
Here's an example of a heavy-duty restrained joint as it's connecting to a valve. This is called an MJ adapter, and it's very common in our industry. That is injection molded and fused right on the pipe. That's another way to do it. I'm going through these pretty quick, guys. This can be done under wet conditions, as you're seeing, which water presence for fusion is not a no bueno, as Johnny Canturi would say. Here's an example potentially of a anchor restraint versus a thrust restraint. Now, we don't always have the pictures we want, and this picture happens to be controlling a water treatment plant mixing plant or mixing concrete area more so than it is a thrust or anchor restraint specific to HDPE, but anchor restraints are going to be at the end or terminal connections as to what we're looking at, and we're going to be looking for reinforced concrete in there. So there are other adapters that you can put into buried concrete that's reinforced. Here's a butt fused wall anchor and then also electrofusion restraints. We did get a question about industry options for you, and PPI just released anchor blocks for HDPE final report in September 2022, which also came with a calculator, but sometimes these tools also need another engineering element for it. So we're 1 minute over. Pete, Brian, Mike, Peter, come on screen as well. Any closing notes of guidance for our team here or those people out there? I'm amazed we've kept all 428 participants all the way to the end. So you guys have done a great job and inspirational itself for those curious about thrust restraint, and you have about 30 seconds a piece to give us some closing arguments. Okay, Pete can talk a lot more than 30 seconds if we don't have it. Mike?
Sure. I would just say, again, like to say thanks for the opportunity to be here. And if people have questions about thrust restraint, do not hesitate to reach out to myself or anyone here on the call or with the Alliance. We're happy to help you, and we want to help you. We want your projects to be successful, because if you aren't successful, we aren't going to be successful. And success is what we want to achieve.
And as far as the takeaway I'd like to offer is PE pipe and any pipe that you put in is very sensitive to soil. It's a soil structure interaction. You got to understand what that is. And as an example, the HDD process, if you are using drill fluid and the drill fluid is below the water table, the drill fluid will become thixotropic, but it's really not going to have any more than a very, very soft clay friction factor to restrain your pipe. So it's not going to restrain it very well. The minute you come above the water table, the friction goes up quite a bit because your moisture content goes down to what the surrounding moisture in the ground is. Your friction goes up. So look at your friction. It is a very real thing. It can help you out, but also watch where your water table is and what your friction is being applied from, what kind of material.
Peter?
Yeah, Alan, you're definitely right. We covered a lot of material here pretty quickly. So certainly, I hope anybody reaches out to anybody on this panel to get any follow-up questions answered. And I think, when it comes to the specific thrust restraint of HDPE, it is a little bit different from some other materials, and we talked about those differences today. But it certainly it can be handled through the design process and just takes maybe a little bit of a foresight to understand the differences in behavior and to design for it. But certainly reach out with any questions.
So just a reminder to everybody, if you'd like a PDH CU, there's a survey at the end. You definitely fill in what state and what type of a certificate that you need. And remember, this certainly will be one of the recorded webinars on the Alliance for PE Pipes YouTube channel. If you need anything else, definitely check out pepipe.org. Peter, Brian, and Mike, thank you so very much for your contributions. This was not an easy ask. This was not an easy topic. And all three of you just really rose to the occasion, and we really appreciate it. So thank you very much, everybody out there, and we look forward to next year when we'll bring out even more. So it sounds like this was a good topic. Peter, what do you think?
Yeah, great job, everybody. We'll see you next year. Look for your PDHs, CUs. If you don't get them, send us an email. See you then.